Welcome to BTEC Revision. In today's lesson, we're looking at elastic constants. By the end, we should be able to calculate the modulus of elasticity and the modulus of rigidity. The modulus of elasticity is also known as Young's modulus, and it is equal to direct stress divided by direct strain. The short form of this equation is capital E equals sigma divided by epsilon, where capital E equals the modulus of elasticity, sigma equals direct stress, and epsilon equals direct strain. The units for this equation is measured in newtons per meter squared, because direct stress is measured in newtons per meter squared, and direct strain doesn't have a unit. This is also known as pascals. Start by writing down the equation E equals sigma divided by epsilon, and sigma is the direct stress, which is the force divided by the area, and epsilon is the extension divided by the length. We have the force value, which is 20 kilonewtons. So we should write down 20,000 because a kilo is 1,000, and that's equal to the force. So we have the force. Next, we need to work out the area. The area of this rod is equal to pi r squared. And we know the diameter, which is 10 millimeters. So the radius is going to be half of that, which is 5 milli, which is 10 to the power of -3 meters. So that's pi times 5 times 10 to the power of -3 squared. So we have the area. Next, we have the extension in the length is 0.2 millimeters. So the extension is 0.2 times 10 to the power of -3. And finally, we need the length. The length is 1 meter. So we have the length also. Now we can just plug in all the values. The force is 20,000 divided by A, which is pi times 5 times 10 to the -3 squared. And that's all over extension, which is 0.2 times 10 to the -3 times by the length, which is 1. And plugging this value into the calculator, I get 1.273 times 10 to the power of 12. The units are going to be pascals. Next, we'll look at the modulus of rigidity, which is similar to the equation before, but the difference here is we divide shear stress with shear strain. The short form of this equation is capital G equals tau divided by gamma, where capital G stands for the modulus of rigidity, tau stands for the shear stress, and gamma stands for the shear strain. The units for this are also newtons per meter squared, because shear stress is measured in newtons per meter squared, and shear strain doesn't have a unit, so therefore the modulus of rigidity is going to be newtons per meter squared for its unit. Now let's look at this example. A steel rod of length 3 meters and diameter 20 millimeters is subjected to a shear force of 100 kilonewtons. The deformation in the rod is measured to be 0.2 millimeters. Calculate the modulus of rigidity for the steel. We will start by writing down our equation, the modulus of rigidity, which is equal to shear stress divided by shear strain. And we know shear stress is equal to the force divided by the area divided by our shear strain, which is extension divided by length. We can plug in our values. We know force is 100 kilo, so that's 10 to the power of 3, and that's divided by the area. Now, since we're using a rod, the area is going to be pi r squared. We know r is half the diameter, so that is 10 millimeters, 10 to the power of -3, and that is divided. And then all of that is divided by the extension. So that's 0.2 times 10 to the -3, and that is divided by the length, which is 3 meters. And don't forget to square the radius because the area of a circle is pi r squared. Plugging these values into our equation, we get 4.7746 times 10 to the power of 12. And the unit is newtons per meter squared. Now pause the video here and attempt this exam question. First, to answer this question, we will have to look at which equation we need to use. Since we're looking at a tensile force, we are going to be using the modulus of elasticity, which is E, and that's equal to sigma divided by epsilon. And we know sigma is equal to force divided by area. So this time I'm going to write this slightly differently because we need to rearrange to calculate the extension. And we're going to divide by epsilon, which is extension divided by length. So if you can see here, we have divide, divide. So this can go right to the top, and we can write this as force times length divided by area times extension. Now, since the question is asking for extension, we're going to rearrange this equation for extension. So we will multiply both sides by little e, and then divide both sides by big E. So that would give us extension equals force times length divided by area times capital E. Now we can plug in our values. So the force is tensile force of 100 multiplied by the length, which is 1 meter, divided by the area, which is pi times r, and r is 0.1 milli. So that's 10 to the power of negative 3 squared, and multiplied by the modulus of elasticity, which is 1.59 times 10 to the power of 13. Plugging in our values into our equation, we get a value of 0.2 times 10 to the negative 3 meters, and that's equal to 0.2 millimeters.